Uh, Good morning, everyone. A very warm welcome to the seventh session of the Green Cementech, where we are talking about energy efficiency in boiler, turbine, generator, and its auxiliaries and captive power plants. We are very happy to have our session chairman, Mr. Pawan Mathur, who will be chairing this session. To begin with, I would like to give a very brief introduction to Mr. Pawan Mathur. Mr. Pawan Mathur is working as Vice President and Head Electrical Automation, Thermal Power Plants and Renewable Energy at Aditya Birla Group. He has more than 26 years of experience, and he handles several areas which includes CapEx, new technology adoption, digitization, energy efficiency, cost regulations, cost reduction, and environmental and safety regulations uh, related to all electrical and automation and thermal power plants. His area of work includes more than 23 integrated plants, 25 grinding units, 38 CPPs, and 7 bulk terminals. He has experience in handling several greenfield and brownfield cement plant projects, and also in maintenance and other management systems. I think with this, I would like to welcome Pawan Mathur sir. Sir, thank you for joining us. With your permission, we can start the session. Thank you.
Thank you, Mehul. So topic for today is efficiencies in thermal power plants, boiler, turbine generators. So that is the topic for this session. And as we all are aware that with the complex situation of high fuel prices or inclusion of solar and other sources, wind, solar, other renewable sources, WHRS, the situation is becoming complex for optimizing the TPP operations. So that is why the energy efficiency is very important for all the cement industry or other industries as well. And that is why we are talking on this specific subject of the energy efficiency. So as far as I understand, there are number of initiatives which all the industry members are taking on their captive power plants. But I will like to name a few which may give us breakthrough or which are giving breakthrough now. One of which can be means AI/ML, artificial intelligence, which we have not explored till now to a greater extent. So that is one point which will be discussed today also. CFD analysis. Many of people, they have not done CFD analysis in boilers. Kiln they have done, but CFD analysis for boilers they have not done. But that can also give us good results and a large improvement in boiler efficiency. Boiler feed pump retrofits. So I'm not talking about new pumps or VFDs, but retrofits of the boiler feed pump, because PLF is reducing, so feed pumps are getting inefficient. So that is one point which came to my mind. Fuel management. How to do a better fuel management, because now we have to use whatever fuel is available. So how do we make sure that our operations are best efficient? Boilers are operating full 24 hours into 7. So that fuel management can give us good results. Biomass or AFR optimization, how we can do. Government regulations also say that certain percentage we have to do. So how do we maximize onto that? ACC interconnection. So we have, if we have some spare ACCs available in our plant, so doing interconnection, we can improve the this vacuum and generate in a better way. SRC bundles. So these are few initiatives which can give us some very good implemented till now. Those can be implemented at various places. So CIA is a good platform. We can understand all these things. Now, going ahead, I will come to the program for today, and I will invite Mr. Siemens Energy, Mr. Raju Kadian, and Mr. Kalpesh. So they will be taking up on efficiency improvement in steam turbines operating on low pressure. That is the topic.
Yeah, thank you, sir. I just share my screen.
Yeah.
Is
You
it
can start,
visible?
sir. Yeah, it is visible. You can start, sir. Thank you.
Yeah. Good morning to all. First of all, I want to thanks the CAI to provide us opportunity to present in this forum. Uh, our topic of presentation is efficiency improvement in steam turbines operating on low steam parameters. I'm going to cover this topic in three parts. One is introduction of the Siemens, second is thermodynamics, third is new technology and development, and fourth one is the solution for low steam parameter, which we have executed, and some case studies. Starting with the introduction, in Siemens, in India, we have more than 3,000 rotating machines, which we have supplied in multiple industry sectors. And we have two manufacturing units in India. One is at Baroda, second one is in Bangalore. The biggest one is in Baroda. We are able to manufacture steam turbines from 9 kilowatt to 175 megawatt turbines. We have supplied single cylinder turbines, 120 megawatt to VII C. That is our capability. And under the umbrella, under the initiative of Making India, we are complete designing, means starting from order acquisition stage to the completion, providing commissioning, erection commissioning, after sales service to our customers. And in India, from Baroda, from last 5 years, we have successfully executed modes and up projects, which are in different industries. And across global, there is a reference of more than 900 successful turbines upgrades in last 25 years. And for other OEMs, we did footprint replacement, around 30 turbines. Now, just coming to the to get some flavor of thermodynamics. Internal efficiency is the important measure of performance of turbines, and internal efficiency, based on this one, normally we supply internal turbines having internal efficiency from 88 to 91%, depending on the size of the machines and inlet stream conditions. Here is the you can see from the graph, which is TS plot. H2 is the important factor, which is the H2 is the enthalpy of steam which is coming out from the turbine. Based on this H2 measurement, we can compare different OEMs. Present the turbine which are running in the market, they have the internal efficiency in the order of 78 to 84%. And we can provide more efficient solution to these turbines. To have just a glimpse of what is the ideal or 100% efficient, what is the heat rate values which we can achieving considering 100% efficient turbine, gearbox and generator. With the inlet stream parameter, as you can see from 13 bar to 350 degrees centigrade with the water cooled condenser, the maximum efficiency which is possible theoretically is 2896. And with the ACC application, like with 0.2 bar, it is coming 3168. So this becomes the base values. If we are considering the inefficiencies of the turbine and gearbox and generator, then this base value changes from it is in the range from the 3500 to 3900 kilocalorie. That's the heat rate value we are looking for. And in the Mollier chart, you can see that the vertical enthalpy drop, it is the isentropic enthalpy, which is the available heat to the turbine to convert into the power. And greater the length or height of this vertical length, smaller quantity of steam will be required to produce the same power output. Now coming to new technologies and development in the field of turbines. Uh, In Siemens, we have different different families of last stage blades. We call it like B blades, SK blades, C blades, E blades, and EL blades. Last stage blades are important both for thermal as well mechanical point of view. And it generally for last stage blades, the last 2 or 3 blades provide 15 to 20% of total power output. And selection of the optimal size of blades based on it is the exhaust stream condition and how much the volumetric flow passing through these blades. So selection is very important. Now coming to the development of the blades, which are coming the HP, MP, and middle part of turbines. There is a continuous and consistent development of program over the last decade. This is with the help of CFD analysis. Earlier, we had supplied turbines with the cylindrical blades, having the constant cross section over the length of the blades. And then next comes the first generation blades with the twisted blades having a different profile at the root, mid, and top level. And the latest one is the 3DS blades, which look like banana shape, and its profile keep on changing, and this give better efficiencies as compared to cylindrical or these twisted blades. It reduces secondary losses in the turbine significantly in the flow path area. Besides aerofoil, other important aspects are the shroud, that is which shrouds are important, and their interstage seal concept is there between the diaphragm and moving blades, and proper design of the sealing concept is important to reduce this leakage. Second aspect in this case is integration of this leakage stream in the main flow, so that this add to the power output. And third one is the root design. Root of the blade should be it should be proper and proven design. Clamping should be of rugged construction. This gives the overview of, as I talked in my earlier slides, like you can make it out from left, that is conventional design, to the improved design. You can find out from the shape of the shroud on the moving blade, which are generally shelf-shrouded blades, and on the shrouds of diaphragms. There are more number of seals are there. These are possible due to optimized design of turbine casing and guide blade carriers to get the minimum thermal expansion values, differential expansion values. Now the brush shields generally we provide in the balance piston area. These are these are costly affairs. Generally, it's we include in the design based on the customer requirements. Its main function is it provide minimum clearances between the rotor and stator. Generally, the clearance value is in the term of 0.1 to 0.2 mm. Now coming to the casing design, in Siemens we have improved casing design and guide bed carrier to get the best thermal inertia of the casing, and designs symmetrical casing from top and bottom half, so that we can get reduce the startup time of the machine, and it is give more flexibility during the load change. And with in the design stage, if customer demands, we can provide also the LTP concept, and we can extend the gap between two major overhauls. Generally, it is 50,000 hours. We can make it 1 lakh hours. That is based on the selection of the material for the guide blade carriers, turbine casing, and the rotor. Now coming to the valve design, old design was with the lot of spring, valve bar, and lot of fulcrums and moving parts were there. Now these things are made much simpler with the new design, so that these can be easily maintainable, or we can switch over also the valves during operation if required. Now solution for low steam parameters. These turbines we have executed, and these are running successfully in the field. It is 20 megawatt machines. It has the inlet steam parameter of 18 ATA, 445 degrees centigrade, and with the injection steam. And we are able to give the internal efficiency of turbine at 88.9%. And heat rate is 3499 kilocalorie. Heat rate we have calculated considering the enthalpy after condenser. Now coming to the part where customer is asking about the part load efficiency. Normally these turbines with low inlet steam parameter, these are without control stage, and they have the maximum efficiency when the maximum steam or maximum flow is going through the inlet flow is maximum. But efficiency reduced significantly as compared to control stage at part load. So we need to use the concept of internal bypass to have the same efficiency. You can see that at 8.55 megawatt, that is the full load, the internal efficiency is 87.3%. And at around 80% load, which is 6.82, it has almost the same efficiencies. So we, by using the bypass method, it may be inner bypass, after 1 GBC or second bypass, we can achieve part load efficiencies. What happens in this one, like in part load, like 6.82, steam is passing from ESP to control valve on the front side and going to the condenser. But at the higher flow, like in 8.5, maximum flow is bypassing the first stage group and going directly in between after stage group 1 to the turbine. We are also able to provide double flow turbines with the steam. For example, it is injection steam, maybe 3 ATA 180 degree. It is going, it is starting from the middle of the turbines and flowing in the both directions. Both side flow paths are identical. We can provide this solution for both ACC and water cooled applications, and with inlet parameter 3 to 20 bar. Now coming to the some case studies. Before going to the modes and up, there's important factors what are driving for the modes and upgrades. One is the, if we want to improve the SSC, specific consumption of the machine, or improve the heat rate. Second one is the adaptation of the new process requirement. Sometimes we have come across some customer which has turbine is designed with higher parameters, maybe 64 or 84 bars. Now they want uh, to make it stable for the low parameter, maybe 18 or 13 bar. So be keeping the same gearbox and generator. If it is a Siemens machine, we provide flow path change options. And if other OEMs, then we are going for footprint replacement. And there's also drive factor. If driving factor is we going from water cooled to air cooled or vice versa. And if a machine is the old, means running for quite a long time, maybe 20 years, then by using the modern ops, we can provide efficiency and retaining back the turbine life cycle. And we can provide the latest technology. Under modern up, we have 4 solutions. One is flow path change. Here we change the components which are come in contact with steam. We do it for Siemens and Siemens licensee fleets. Second option is the footprint replacement. Footprint replacement with the minimum modification in the foundation and layout of the machine. Third one is the partial revamp, where we change the we do minor modification like removing 1 or 2 stages, for example here, to increase the swallow capacity of turbine. Fourth one is the control upgrades. This is the one case study where we have enhanced the power from 7 megawatt to 8.8 megawatt. Here we have supplied this machine to the customer. After running after 2 months, he realized that he has extra steam available with him, and also he has higher inlet steam parameter. Then he approached us. We did basically complete flow path, complete TG train replacement for that customer. And for this complete site execution took only 18 days, and payback period for the customer is only 9 months, and he gained 1.8 megawatt with that extra steam. Now coming to the second case study, where it was our supplied machine with inlet parameter 84 and 505. And after running for some year, 2 or 3 years, then customer shut down the machines for shut down the machine for quite long years. Then he realized that he can operate this machine or utilize this turbine for low steam parameters. Then he approached us. We changed the flow path in the machine that is suitable for low steam application, and we retained the same gearbox and generator. And in this case, the efficiency of the machine is 87.71 and heat rate is 3499 kilocalorie. This is a project where we are giving solution. It is 16 megawatt project where we are giving solution with 2 ESVs with the wheel chamber bypass and inner bypass. You can see that internal efficiency of machine is close to 90%, and it has the multiple valves. This is just a reference list for where we supplied turbines running with waste heat recovery boiler parameters. Now, what is the benefit customer is getting with the modes and up? That is the optimized performance. This is based on it is he is getting with the modes and up the improved efficiency, long life cycle, increased lifetime, extensive test and improvement records, adaptation to new steam parameter and exhaust conditions, high reliability, reduced startup time. With this, I end up my presentation. Thanks to CIE and thanks to Pawan Mathur. Thanks, sir.
Okay. Thank you, Mr. Raju. And I would just like to summary your points. One of the things you emphasize that 2 to 6% of improvement scope can be there in Siemens turbines through various modifications you have shown case studies on. Blade selection and blade design, sealings, turbine casing and guide blade carrier, wall designs. So this is the scope of improvement where efficiencies can be improved. You also suggested that part load management can also be done using the bypass techniques.
Right, sir.
And you told about various driving factors which are the causes for improvements. And then you also let us know feasible solutions, means like flow path or stage removals or footprint. So in fact, you guided us on how turbine can be improved in the overall efficiency cycle. So thank you, Mr. Raju, for that. I'll come back for if there are any questions at a later stage.
Sure, sir.
Thank you very much.
Thanks a lot.
Yeah. And I think next I invite Mr. Manoj Gupta from Atlas Copco, who will be delivering on latest developments in compressed air system. We all know that compressed air is a very high energy consuming equipment in our TPPs. So what are the latest developments? What are means kind of compressors, screw compressors, or any other kind of developments which are taking place in compressors that will be delivered by Mr. Manoj. Mr. Manoj, please.
Yeah, thank you, Pawanji. Thank you, CII, for giving the opportunity to present. I will share my screen. Is it visible?
So can you make it full screen?
Yeah.
Yeah.
Yeah, good afternoon, good morning, all of you. So today we will discuss about the energy efficiency in compressed air system. So I will touch upon all the possible option where we can save the energy. To start with, just one slide for Atlas Copco. Atlas Copco is established in 1873 in Scotland, operated in India since 1960, and we have global presence of more than 182 countries and around 39,000 employees working in more than 90 countries. We at Atlas Copco have 4 divisions like compressor division, vacuum technique division, industrial technique, and power technique. So mostly we are focusing on the compressed air system. So in compressed air system, we are working on the industrial air division, oil-free compressed air, professional air, gas and process division, and medical air solution. Like we believe in the innovation, so we have different complete product range available with us so that we can provide the most energy efficient solution to our customer. Like we have divided our product portfolio in 3 categories, like low pressure compressor. Low pressure compressor, it start from the 0.5 bar to approximately 4 bar gauge, and we have all-free lobe compressor, all-free screw, and all-free centrifugal. Same as with the medium pressure also, we have all-free tooth compressor, all-free screw, all-free centrifugal, and oil-injected compressor. And for high pressure, that is up to all-free piston compressor is there. Medium pressure range up to 13.5 or 14 bar. That is a compression overview. For air treatment, we have different type of dryers like refrigerator dryer, desiccator dryer, rotary drum dryer, and all the filtration, which includes the HOC dryer, blower, all type of dryer we have available with us. And the generation, we have on-site nitrogen generation, we have oxygen generation also. And then energy recovery, we have energy recovery option available in all type of compressors. And like stress system monitoring control, like we can optimize the system where multiple compressor is there. So we can optimize the best solution which can be delivered. Agenda is we will discuss about the below points like quality standards, why energy is important in compressor system, potential energy saving in compressor system, product portfolio, quality air solution like dryers, air blowers, optimizers for energy recovery, and energy efficient compressor system, how it should be. Okay, so air quality class. Air quality class is defined as the ISO 8573, which is the 7 priority class. I start from 0 to 6, like whenever we discuss about the class 0 certified and this thing, what does it mean? So we will discuss like, for example, if the class 1 to 1 is there, so what does it mean? So first digit, first number represent the solid particle content in the class, in the air quality. So 1 means the air quality in terms of solid particle should be below in this range. 2 means 2 denote the second number represent the water class. So class 2 means the water moisture content in terms of dew point, it should be below -40. In terms of measuring the pressure dew point for should be -40 degree centigrade for class 2 air. And last class 1 means the maximum oil concentration in the outlet air should be less than 0.01 milligram per meter cube. So that is the complete classification. We told that our compressor is class 0 certified for oil content. So that's why we are offering the non-lubricated class 0 certified compressor, which is mostly reliable and we can offer. Why is energy important in compressed air system? Like you know that from operating point of view, the compressor room is the largest electricity user in the whole equipment, and the 15 to 20% power plant electric consumption is in compressed air system. And energy saving is energy is up to 80% of compressor life cycle cost. If we can see the total cost of ownership, like 80% is the energy cost, remaining is the maintenance investment, and the installation cost will be there, which is equivalent to 99% of CO2 emission. For a power plant of 800 megawatt into 3, by reducing the 5% compressed air power consumption, and the saving can be 5 lakh kilowatt hour every year. So we can see how much energy saving is important in the compressed air system. Just to note, like not to the presentation, if you have any queries and doubt, you can put it in chat. So my colleague or I will give the answer simultaneously. So this is the typical thermal power plant layout. So we have the identified where the compressed air is used. Like for instrument air, we compressed air used up to 8 bar, and the demand is 50% stable and 50% variable. And the dew point requirement is minus 40 degree atmospheric dew point. Like coal handling plants, dust separation system, and this air is required. Now we can say pneumatic conveying air. This is pneumatic conveying where the low pressure air is required. So we have the solution for low pressure also, that is up to 2.5 bar, and that required all free air, so that oil should not be mixed, and there is no dry requirement is there as such. So and for service air, like this is the real demand, which is 100% variable demand. So there is all free compressor is used, and the flue get depressurization. There also the low pressure air is required with the no dryer and all free requirement. So this is the layout where different type of air, different type of pressure is required. So we can provide all the type of compressors and the pressure based on the consumption pattern. Yeah. So this is the graph where we can see the energy saving potential. So in what area we can save the energy. They to start with the CAS audit, like compressed air system audit. So we have the facility to audit the compressed air system, where we can analyze your demand, analyze your pressure requirement, your working pattern, how much variation is there. So demand point side and generation point. All this audit we do in-house with our dedicated team, air audit team. So this is the, by doing this, we can analyze what is the requirement, and then we can propose the solution. After that, the core technology. Which technology should be used to get the maximum energy efficiency and lower cost of ownership? So that we decide of the compressed air audit, like how much your demand is there. Like we have all the technology available in-house: screw, centrifugal, piston, scroll, all this technology. Now, based on the air pattern, so we decide the dry technology, like whether it is demand is the fix or demand is the variation. So based on the air audit, and we can get the data like how much your load variation is there throughout the day or throughout the month. So then we can propose the solution with the fixed speed or the varying VSD technology. After that, we have energy efficient energy air treatment. Like when in instrument air, you don't air should be the dry, so that it will not affect the instrument and the surround walls and something. So for that, we have different type of dryers available with us. So dryer is different type of dryer, like refrigerant type dryer, low reactivated dryer, heatless desiccant dryer, and HOC dryer, which is heat of compression type dryer, which is the most energy efficient dryer as of now in the world. So based on that requirement, we can propose the dryer. Now the optimization, where multiple compressor is there. So we should, if there is, we have the facility with the controller, like to reduce the pressure band. Like when multiple compressor is there, so we will normally it will run one by one, then two, then three, then four. It is in sequence. So by doing this sequence, we have huge pressure drop, because we have to increase the pressure band. So to optimize that, we have optimization, so that we can reduce the pressure band, and we can propose the most energy efficient solution, combination of energy efficient solution, which can deliver the set pressure, desired required pressure. Then we have energy recovery. Energy recovery, it means you can get the you can recover the energy of compressed air compressor system in terms of hot water. which can be used in the boiler feed or the space heating and or shower and anything, canteen, anything. So we have the energy recovery available for screw compressor and as well as centrifugal compressor in both. Now the blower technology, like where the fly ash conveying, you require a low pressure compressor. So for that we have blower available also and low pressure compressor available also. And the SmartLink, like SmartLink, we have the SmartLink features inbuilt in all our compressor, where you can get the flow pattern, the consumption pattern, the energy pattern, all the alarm, warning, shutdown. You will get the trigger in form of mails or SMS, and that is the free of charge for first 3 months. And that's the features. You can get the license and you can get the report, complete air audit report, where how much energy you are getting, how much consumption you are doing. So you can get all the graph also. So basically it is monitoring device. You can monitor your compressed air system, how efficient they are. Typically compressed air system, like in the normally power plant, we should be like this, like normally the fixed speed or centrifugal compressor will be there, then the piping, then pre-filter filtration is there, then heatless desiccant dryer is there, then fine filter, and then the wet air receiver, then dry receiver is there. So we can see the pressure drop between here. If we generate the 8 to 8.5 bar, we will get the 7 bar at the receiver outlet. And the pressure drop, why it is pressure drop? This pressure drop is because of the pre-filter, then the desiccant dryer, then the fine filter, and the pipes, bend, tees, and walls, and wet air receiver, and unwanted leakage, because over the period of time, all the joints tends to leak, either in 2 years, 3 years, lesser. So there is a chance of leakage. So by adding this, complete the pressure drop of this system is approximately 1.5 bar when it is new. It can go up to 2 bar also when the filter is choking and this thing. And we know that the 1 bar at pressure energy saving is equivalent to 7% electrical saving. Like if we can reduce the pressure of compressor system by 1 bar, so we can save the 7% energy consumption. So for all type of varying load pattern, like base load, minimum load, top load, this is the just example. Like we have developed the chart where in the 24 hours the demand is varying in, you can see, in the range of 550 to 1500 CFM. Then in the day hours, that the demand goes up to very high. Then again in the evening hours it will be more or less stable. So with different demand technology, we have different technology. Like for the base demand, we can offer the centrifugal compressor, which is most energy efficient at the continuous load basis. Then for the fixed speed, fixed pattern, we have screw compressor, which can give the load and load technology, because demand is fixed. So you can use the centrifugal compressor for base load, and for top of load, it is a screw compressor. And you can use the VHD compressor for the varying load. So the combination of these three technology will give you the most lowest cost of energy. In terms of ACR, it will give the best ACR by combination of this. We call it the hybrid combination, which is the most energy efficient combination considering the load pattern. We have different core technology available in-house with us, like all-free piston compressor, all-free and all-injected piston compressor for high pressure application. We have scroll compressor for very low air demand to very less CFM. Then we have tooth compressor that is also available in all-free, which can give up to, for a small compressor, like up to 200, 300 CFM. This is the best technology available. Then we have all-free screw compressor available, which is up to 100 kilowatt also. Compressor blower, and all the technology are available, like fixed speed and variable load also, VHD also. We have all injected compressor also available with us. Fixed speed VHD, both inbuilt drive is also available. And then last centrifugal compressor, which is all-free turbo compressor. The range is We have complete range available starting from 400 kilowatt to 6,000 kilowatt, all this available. And that is all in-house manufacturing with us. Like based on the national mix, like we have different technology available. So based on the flow pattern, we have scroll compressor, then tooth compressor, and a screw and centrifugal. Based on the flow, we propose which is the best combination in terms of ACR. Now you can see for higher flow, the centrifugal technology is best. For the lower flow, the scroll and tooth compressor technology is the best technology which can give you the lowest ACR, specific energy consumption. Just to introduce a little bit, like rotary tooth compressor, we have all-free two-stage tooth compressor available with us, starting from 15 to 55 kilowatt. It is plug and play. You can see this is a completely small box, which is we have option of the inbuilt VST also. We have option of inbuilt dryer also. In the dryer, we have both the option like refrigerant type dryer as well as HOC type dryer. All types of this is available with us at the in-house in the single skate. Second is oil-free screw technology. We can guarantee the 100% oil-free class 0 certified with the option of inbuilt HOC dryer. You can see the dryer is also inbuilt. We have option of the inbuilt VSD also. So you can see the plug and play design with the lowest maintenance cost, and the advanced feature is advanced touch controller, superior screw element with the special rotor coating. So it will give the life of more than 40,000 hours. And we have provided the SS coolers and the EGMA Q15 gears, which can give you the cooler life approximately 8 to 10 years and much more. And with the help of VSD technology, we can save up to 35% energy saving. And we have the VSD available with 75 to 80% turn down. So that is very important. Like if the load demand is very varying, so you can use the VSD and you need not to waste the unload power. For centrifugal air compressor, like we have that is also class 0 certified energy efficient compressor, which is compact in design. You can see it is very small and small footprint, and we can see the 1% gain in energy result in yearly of 1.2 million IN, and that is this calculation is based on the 2200 kilowatt unit running with the 8,000 hours per year. You can see with this technology there is class 0 certified oil free, so zero risk of oil contamination, zero risk of damage of unsafe product, and zero risk of loss of operation downtime. We have central technology with canopy and without canopy both. The main feature is servo motor controlled IGV and BOV, which gives the better turn down. In certain range, you can see the turn down will be in the range of 25 to 40% also. There is no pilot air requirement because it is a plug and play, so no external dependencies there. That is just you have to put the electrical supply and cooling water inlet outlet connection. You can run the compressor. And noise level is with canopy, it is in the range of 72 dBA, and without canopy, it is 85 dBA. We have SS intercooler aftercooler, which can give the life of cooler, which is more than 8 to 10 years. We have IP55 motor, which is high efficiency class, and the control system. And we have the impeller used with the SS impeller, designed by using the CFD software computational fluid dynamics, so that we can achieve the better turn down.
Try to sum up in next 1 to 2 minutes. One minute.
Yeah. You want to ask anything, something?
No, to manage the time now. So
Yeah.
try to sum up in next 1 to 2 minutes maximum.
Yeah. I will complete in 20 minutes. It is 16 minutes. I will complete in 20 minutes.
Okay.
Quality air solution, we have all the type of available, like all type of dryer, heatless dryer, lower reactor dryer, refrigerant dryer, HOC dryer, all this available with this in-house. Energy saving in the rotating dryer, we have HOC dryer available with the zero loss. There's no electrical consumption is there, no wall, no fitting, no loose desiccant. And the new innovation is guaranteed dew point with new MDG dryer at zero power, zero pressure loss and zero power condition. The dew point is -40 pressure dew point guaranteed. This is just example with the dryer technology like heated dryer, then heated low reactor dryer compared to HOC dryer. The saving is approximately 30 million INR. If you require a more detail, we can give you the detailed presentation based on your requirement. Blower that is available with us for the low pressure blower, and this screw blower gives the energy saving up to 35%. If you can see the we have see the comparison of our low blower versus the screw blower, then the energy saving is up to 35%, and it is certified by the TV also. Then we have optimizer available with us, which can give you the where multiple of compressor is there. Then we can use the optimizer, which is fulfill the requirement of Industry 4.0. And you can see the data computing up to 1 month, and we can connect up to 30 compressors that we can escape. Like we have energy recovery unit available with us, like for multiple screw compressor is there, so we can use the heat recovery, which can be used for the boiler feed water. It is available with our compressor system. Now centrifugal compressor is also available with the energy recovery unit. So whenever you have the requirement of hot air, so you can use the centrifugal with heat recovery. So this is the complete air solution, like what it should be, like where the demand is there, like screw compressor, or if centrifugal compressor or screw, then fixed speed compressor, then VHD compressor for varying demand, along with the zero loss of HOC dryer, so that no energy consumption and power loss. Then optimizer to maintain the lowest operating band, and then the energy recovery. By doing this, you can save up to 20 to 25% energy saving by all this combination. That is from my side. If you have any question, you can ask in chat, or if you have any doubt, you can come back to me. I will share my mail ID and phone number in this. So, some myself.
Thank you, Manoj. Just to have the summary for all of us, Mr. Manoj told us first about air quality in terms of solid content, water, and oil. Because if we don't maintain that quality required for our equipments, then we will have losses at other places and maybe some equipment damages or breakdowns. Second, he told the importance of energy, because he said 15 to 20% in electrical consumption is only due to compressed air in thermal power plants, which is true, and that is why this is very important. Then he emphasized on various optimization and compressed air audits to understand what is the current stage. He told us about dry air, how we can make the air dry and with an optimized parameter. He talked about HOC dryers, which are he focused on that this can be a good option. Then he talked about core technologies of compressor, single stage, double stage, screw, piston, and he told us about which compressors to be used at which place and why. So he told us everything on that. Then optimization part, he told us about that using the digitalization, VSDs, we can do the optimization of the air if we have number of compressors 3, 4, 5 in a single line. So how we can optimize that? He told us that. Then he also told us about energy recovery. We all know that compressors generate a lot of heat. So how we can recover the heat? So this is one area where not very high amount of work has been done in cement industry or any other industry. This is one again one area. He also told about blowers. Nowadays, in place of compressors, we are using blowers for say low pressure applications. So he also gave some idea on blowers where we can use, and he emphasized that 1 bar loss is 7% energy loss. So that is the key message he gave, and asked to do various initiatives in the compressor system. Thank you very much, Mr. Manoj. And now I invite, thanks a lot. Mr. Naman Gupta, who is from Equilibrium Energy, and he will be taking a very relevant topic, which is coming up very fast, and we started implementing in our cement plants, which is AI for flexible CPP operation and reliability. So that is one important area. So how we can save the heat rate, how we can improve our reliability using AI ML techniques. So I invite Mr. Naman. Naman, please.
Thank you for the introduction, Mr. Mathur. And thank you, CII, for giving us this opportunity to present Smartsense. I would just like to share my screen. So my name is Naman Gupta, and I have been working with Equilibrium for past 7 years, and we have been delivering sustainable prosperity to our clients. So the company's name is Equilibrium, and we call our product, the platform we call Smartsense. Through the course of time, I will be just briefing you about our company, and briefly I will touch upon the approach we take to develop certain use cases, and then we will have a deep dive into how we have implemented turbine or power plant integrate power plant with Smartsense. So Equilibrium is a 10 years old company incubated out of IIM Ahmedabad. Initially, we started with energy monitoring, and slowly, once the data started collating, we developed an IoT platform. And based on the data we developed a certain algorithm, predictive maintenance algorithms for certain assets like chillers, chillers, motors, and some other assets we have. And then we have some international recognition from Ashton, WWF, UNFCCC, etc. for energy efficiency and sustainability, etc. We are a team of around 65 people based all across India, and it's a domestic product which we are taking international. We have our presence in UK and US also now. These are some of our global partners like Schneider, SAP, etc., with whom we work internationally. Then these are some list of our clients and our partners like Amazon Web Services, JLL, etc., which help us, who are helping us take this product international. This is the team which we have, our management. Mr. Chintan Soni and Harit Soni are the founders. Mr. Shugato Guha heads the delivery and operations. Mr. Ibrahim Burgess, he has an experience of around 35 plus years with Schneider and Conserve. So he heads our sales, and Purvi Maheshwari, she's our CFO. And we also have a team of domain experts who help us, embed their expertise into algorithms so that we can, have a great solution, a great AI or ML algorithm which can be used consistently to improve capability of Smartsense. So as an overall approach, we have 4 stages in which we generally take up a use case. So what we have seen is that there is a gap of understanding between the client and how a software can be perceived. So first of all, we do the consulting phase, which is business impact matrix. We create a business impact matrix saying that this is the amount of saving which we can deliver. And then we do the detailed infrastructure and gap assessment. So that's the first phase. And for this, we consume domain experts and our internal delivery experts also. The second part is deployment of Smartsense solutions on field. Uh, this is the part where the business matrices or the KPIs which have been decided by the plant and us are implemented onto the platform, and the dashboard reports and alerts are created. So that's where the platform is created for the client. The third part is program management, where our delivery manager and the analyst, helps you set the right kind of alerts and also takes the feedback on what kind of business impact has this platform delivered. So we are in this process with you. Our analyst and our delivery manager and key account manager make sure that all the initiatives or the recommendation which this platform has given are acted upon. And then the fourth part is review and impact. So we conduct quarterly business reviews, half-yearly business reviews to review what kind of saving have we achieved. So which, help us keep on improving the solution. Like in the first phase of a project, if we have just implemented and we have got 50% of our savings. So how how have we achieved those 50% of savings, and how can we work towards achieving the next 50% of the savings? And that's how we encompass the 360-degree approach for developing a solution or a use case. On similar lines, we have developed a use case for CPP, turbines, conveyor belts, etc. And it took us around 6 months' time to deliver this project. So generally, when we are, approaching such a platform, our question is, what are the value levers, or how can we, what impact do we have of these platforms? So deliverables I have already talked about: data acquisition platform, report, consultancy. The basic impact areas through such kind of platform is improvement in manpower optimization, energy optimization, maintenance cost, and also improved uptime and availability. Then about Smartsense, it's a complete full stack solution. We have the capability to extract data from existing sensors, as well as deploy sensors and get the data from those sensors. And we can also integrate with existing DCS, historians, ERPs, etc. And for this interaction, we use our own gateways, which communicate data on GPRS, or it can be a LAN-based application also. Then this data is transferred onto the cloud, and it's a AWS cloud. It's a public instance, our own public instance, on which you can access your data. And then after the data comes onto our platform, we have a platform called Smartsense, on which you can, visualize your data. You can have reports, you can have alerts, and also we analyze this data so that key insights can be generated, and it can be helpful for our people, maintenance people who are using this data for certain applications. So it's a complete full stack solution which we have to develop certain use cases. Yeah. So our vision is of partnership and alignment with our client, where there are 5 steps which we generally take to develop a use case. First is accessing whether the sensors are available or not, integrating it. Second is data acquisition, where the integration work happens. Third is creation of the platform. Fourth is third-party integration, like if we have production data or any other data sitting in elsewhere, how to bring that data onto that platform. And the last part is, delivering the business use cases like quality improvement, process improvement, performance and efficiency improvement. So apart from the insights being given by the platform, we also do site walkthroughs, and our domain expert teams, they give a report also, database report, which suggests the measures which can be taken. So that's the approach we generally take to understand the entire factory and develop a digital twin which can be established onto Smartsense so that you can benefit completely out of it. Moving on, I would just like to start with this case study which we have implemented for a CPP in Goa. And we did this, we started this project 6 months back, and we had four equipments, I can say: ESP, electrostatic precipitator, BLT, bell-less stop, turbine, as well as conveyor. The data acquisition for all of this happened through a historian. So we integrated Smartsense to a historian. Data was already existing. And in case of conveyors, we added a certain vibration sensors. And for those vibration sensors, we acquired the data from the field itself. Those sensors had some Wi-Fi and we acquired the data from field itself. After getting the data, we developed, I will just, after this presentation or this case study, I will show you the live platform also on which we have developed it. After getting the data onto Smartsense, we developed certain screens and we had direct and indirect methods of efficiency calculation for turbine on the platform. And, the basic success criteria of all of these four projects was: for ESP, it was to reduce the downtime. For BLT, it was also to reduce the downtime. And the turbine, it was to improve the heat rate. And the conveyor belt, it was to improve the capacity utilization. So after the data started coming, it took us 1.5, 2 months time to set up the benchmarks and develop the KPIs of or the standards based on the actual data and the design parameters. And once that data started coming, we went back to the client that this is the saving potential which we have seen through Smartsense. So I will come on to the saving potential also after I have shown the platform to you. I hope my screen is visible.
Yes, yes, it is visible.
So this is what we call asset library. Here, any kind of asset, whether it is BLT, HESP, conveyor, turbine, AHU, chillers, etc., can be integrated. It's a self-learning library, and it is classified in various classes. And then, if we click on any one of this, let's take the example of the turbine. We will get all the turbines which are available in your unit or group. And once we click on the turbine part, you will get the details of the entire turbine, like what are the rated details of the turbine, what are the overall performance parameters. Like here you can see the heat rate through enthalpy method, through loss method, loss due to condenser, turbine efficiency, loss due to parameter deviation. Then what we understand is that there are multiple parts of a turbine, like cooling tower. Sorry, just a minute. Yeah, so there are multiple parts of turbine like cooling tower, deaerator, etc. So we give individual performance and efficiency of those individual equipments also, which help reduce the overall heat rate of the turbine, right? So as you can see, these are the heat rate of enthalpy method, heat rate through loss method, etc. And heat loss through condenser, we have calculated heat loss on the account of parameter deviation, turbine efficiency, then loss due to LP heater and deaerator. So all these parameters are available for our supervisor or the turbine operator to visualize consistently. And the basic difference between a historian or an existing monitoring system is that it can hold the data up to 3 months only. But on this platform, you can access the data of an entire year. So that's where the data analytics layer chips in. And as I was telling you, there are different parts like condenser, deaerator, LP heater, cooling tower analysis, etc. So all those parameters of condenser like back pressure, exhaust temperature, input temperature, output temperature, chill water input temperature, output temperature, delta T, all those parameters can be monitored separately. So that we can, if there is any deviation in the heat rate, we can calculate why that particular deviation has happened. Is it due to the condenser, due to deaerator, due to LP heater, cooling tower, or what is the specific reason? That's the importance of, having the performance and efficiency of each and every component of the turbine. Then we can also have the asset history, like you have done some maintenance work. You can log on to the system and add that data and you can download that data to check whether the PPM schedule, predictive maintenance schedule, or is being done properly or not. So that's the live demo of the turbine which we have developed. On similar lines, we have developed it for boilers, conveyor belts, as well as the BLT. And you can have a look at each of the key parameters which are available on the platform. So as you can see, we have delivered a total saving of around rupees 206 million to this platform. And in the turbine heat rate optimization, basically we reduced the heat rate from 2915 kilocalorie per kWh to 2498 kilocalorie per kWh and per kilowatt hour, and the estimated potential saving was around 180 million per annum. And the basic critical insights we delivered was from the condenser and the cooling tower, the back pressure was not very well, and the cooling towers were not working efficiently. Then in the conveyor productivity, also we increased the overall efficiency by 3 to 5%, and the overall saving was rupees 22 million per annum. Here, the critical insights triggered by Smartsense were current and voltage imbalance, section-wise, roller-wise vibration deviation. And we had some warning alerts for drive of the motor, standby motor, plumber, and etc. And then HSP and BLT, we had this commitment of no breakdown for 6 months. HESP had some, HESP had some fire problems, and whenever there was a fire, they had to troubleshoot, and the plant used to shut down. After implementation of Smartsense, we gave them alerts on temperature, oxygen level, dust concentrator, etc. And through those alerts, they were able to gauge if there is any possibility of fire in next 10-15 days, and they used to maintain the system earlier, and they were able to save around 4 million per annum through this platform. Then BLT also had basically to avoid breakdowns, and we had an estimated saving of around 0.15 million in the BLT use case. Yeah. So I think that's all from my side. I'm happy to answer any questions later, or you can maybe write it on the chats. So thank you for this opportunity, CII and Mr. Mathur.
Yeah. So thank you, Mr. Naman, for giving us overview on your company and AI technology and use cases. So just to summary this, first you told us about how you are approaching the projects, means business impact, solutioning, setting up the KPIs and then monitoring. So that is the approach which is of course right, because otherwise project may go haywire. That's right. Then you also told us about what are the areas you can contribute in, like manpower, energy, uptime, quality. So lot many areas where your solution can work upon. Then you told us about your technology, which is the platform is known as Smartsense, which can interconnect various sources of information, whether it is PLC, DCS, or to your cloud, or many other EMS system, or any other system which it can take information, and that then act upon analysis can be done. And you also informed us that the technology which is also nowadays it is a proven one, digital twins, where you do analysis for each and individual equipment, dereator or turbine or boiler or all the components, compressor, etc., as well as you can do the whole analysis for full functional analysis of the TPP. So that is what we can get. You have ready-made asset libraries which are plug and play type. So immediately it can start working in the learning mode and then analyzing mode. It's a comprehensive system. You told means maintenance can also be attached to it, depending on the recommendations provided by the system. And you also told us about the case studies where substantial benefits have received 200 millions per annum of heat rate saving, and then conveyor productivity improvements, etc. So thank you, Mr. Naman, for bringing out all this information and experience to us, to all the participants. Thanks a lot. Now I hand over to Mr. Mehul for taking up on heat rate improvements in CPPs. Mehul.
Thank you, sir. I'll just share my screen. I hope the screen is visible, sir.
Yes, yes.
Yeah. Good afternoon, everyone. Welcome to this Green Cementech, where we are having the session on captive power plants. So I'll be talking about CI's experience with several captive power plants as well as the bigger power plants, and I'll try to bring in ideas and case studies which can be adopted by captive power plants to improve the overall heat rate. So this will be the flow of presentation, the agenda for the presentation. I'll start with introduction, then I'll have best practices for boiler efficiency, turbine heat rate, something on EPC. Then I have 2 or 3 ideas which the CPPs can adopt from the bigger IPPs and can implement in their plants. And finally, a list of few miscellaneous best practices in maintenance, predictive maintenance, and improving the overall reliability of CPPs. To begin with, I like to talk about the performance analysis of cement sector CPPs. So in a recent study with Bureau of Energy Efficiency, we actually did a study on almost 73 cement sector CPPs, and we found out the following points from it. So if we see the overall installed capacity of all CPPs from all sectors is around 76.2 gigawatt. Out of that, around the cement sector contributes to around 7.2 gigawatt. And if I talk about the performance levels of the selected or the studied CPPs, the average gross heat rate for all the 73 units on an yearly basis, that too with a weighted average heat rate, was around 3273 kilocalories per kilowatt hour. And I would like to point out the minimum which we saw was around 2770. The average PLF for the entire sector, the cement sector, was around 71%. The average APC was 9.24%. And we also tried to check what could be the overall emission intensity of the captive power plants in the cement sector. And with the numbers, we were able to calculate it at around 1.267 kgs of CO2 per kilowatt hour. I mean, just for a quick reference, not to make any comments on this, if we compare this to the grid emission intensity, it is around 0.79. But maybe that is dependent on a lot of other things. For example, the grid has a lot of renewable energy. It has a lot of bigger supercritical and bigger thermal power plants. Energy efficiency, as we all know, is really important for captive power plants, especially in these scenarios. We did a quick analysis of the performance. So what we have observed is that the boiler efficiency is pretty good and lies in the average range of around 85%, where the CFBCs are on the little higher side, 86, 87 also. While the AFBC boilers, they have a little lower boiler efficiency in the range of, let's say, 82, 83 as well. The turbine heat rate is in the range of 2750. APC cement sector has been doing really well in this area, but still there are few plants which have scope to further reduce. The average lies between 7 to 10%. These numbers are for Indian coal, I would say, and PLF is around 70%. If I talk about some of the issues which are being faced by CPPs recently, I would like to talk about the high fuel cost, especially in the last 1 year where we have seen the fuel cost almost double. I mean, the plants have been really impacted on this by this. Lower capacity utilization, we have been seeing several plants lower than 70% also, which really impacts their overall heat rates. I mean, the heat rate has been really high for many plants now. So if we talk about improving the overall heat rate, we have to have a significant focus on all the major areas. We need to have focus on boiler efficiency, turbine heat rates, APC, as well as the overall O&M practices. How you are actually running the plant is also equally important. So with this, I would like to go into each of these areas one by one. I'll start with boiler efficiency. So boiler efficiency, as you all know, there are around 6 major losses. The dry flue gas loss, loss due to moisture and hydrogen in coal, loss due to moisture in air, loss due to incomplete combustion, loss due to unburnt in fly ash and bottom ash, and loss due to radiation. Now, out of these losses, there are certain points which I have mentioned. I'll share these slides with you. You can all go through them in the details. But if we talk about the losses which are in the control of the plant people, are one is the dry flue gas loss, which contributes to around 6 to 10%. I mean, if the plant performance is good, it will be in the range of 6%. If the plant performance is not very good, the boiler efficiency is high, that would be on the higher side, around 9 to 10%. There are several actions which can be taken to actually improve upon the dry flue gas loss. Your flow dynamics in the furnace, how you are maintaining the balance of primary air and secondary air in the furnace, your furnace condition as such, your nozzle condition, your bed condition, your flame. I mean the actual flame in the furnace, how it is, how properly distributed it is, whether the fluidization is happening normally or not. There are no, we should ensure that there are no accumulations in the boiler. So accumulations in the furnace in terms of clinker and all. So these are the things which actually impact your dry flue gas loss. Then again, the another thing is regarding the incomplete combustion, which is also in some ways dependent or I mean is under the control of plant people. So, what is the carbon monoxide percentage in your boilers? In good plants, we have seen lesser than 20 ppb, but in some of the plants where the oxygen levels are not good, the combustion is not happening properly, the CO can increase beyond 300 ppb also. Then loss due to unburnt and fly ash and bottom ash. This is also something which is again in the control of plant people, and plant people can actually work on this to actually improve the overall boiler efficiency. Again, similar to dry flue gas, this also is in some ways related to overall combustion in the boiler, the fluidization in the bed temperatures, ratio of primary air to secondary air, how your secondary combustion is happening, what is the draft in flue gas, again the balance of air from right and left hand side if in case of double entry flow into the boiler. These are some of the things which actually impact your loss due to unburnt and fly ash and bottom ash. And the last one, which again is in some ways in control of plant people, is maintaining better insulation conditions across your boiler. If you are able to maintain proper insulation conditions, if your surface temperature is not more than 15 to 20 degrees Celsius of the overall ambient temperature, then you can always maintain low radiation losses. Beyond this, another thing which actually impacts your overall cycle efficiency is the DM water loss, which is not controlled, which is not mentioned in this slide, but I'll cover that in a later slide. Next, I would like to move on to a case study on air preheater performance. I always say whenever we are interacting with plant, I always say for boiler, air preheater is the heart of boiler. All your major performance parameter, be it dry flue gas loss, be it unburnt, are in some ways or the other related to your air preheater performance. So always ensure that your air preheater is having minimum leakages. So in this particular case studies, the plant team, this is a case study of a 61.5 megawatt CFBC boiler. Uh, they observed that there was a huge distribution, improper distribution between primary air and secondary air. The difference between oxygen levels at APH inlet and outlet was also high. The primary air and secondary air temperatures were on the lower side, and the ESP inlet temperature was also lower. Now, this gives you a false indication. Actually, when there is a leakage in the air preheater, your ESP inlet temperature would actually reduce. This will show you a wrong indication that your boiler efficiency is on the good side, but that is not the case. Similarly, as I told you in the earlier slide, APH also will impact your unburnt and fly ash and bottom ash, and overall your boiler efficiency will be on the higher side. So the plant team went ahead and did the APH leak test in all their units, and they identified these kind of leakages in the boiler. After the leakages were identified, they went ahead and did a complete rectification. Wherever possible, the APH tubes were dummied and the damage was also removed. If you see, this was the overall before and after performance. I'll not go into all the numbers, but I'll definitely give you few numbers. For example, if you see the earlier difference between the inlet and oxygen outlet, the point number 7 and 8 was 3.6 and 8.7, which was later equalized to 4.1 and 4.55. Almost no difference between inlet and outlet oxygen. Also, if you see the primary air temperature and the secondary air temperature, both the temperatures increased by almost 20 degrees Celsius. And if you see the unburnt in bed ash as well as the fly ash, almost reduced to half the levels which were before the leakage. This shows the improvement in overall performance when your air preheater performance improves. Next, I'll move to turbine heat rate. Turbine heat rate, this is one of the recent, I won't say this is a case study, but this is more of one of our recent studies in a cement plant CPP, where we come across this parameters. I think Siemens can also maybe comment at the end of the session on these. So what we identified was the overall specific steam consumption of both the turbines was on the higher side. If you see the specific steam consumption of first turbine and the second turbine was around 4.9 and 4.48 respectively. Even the isentropic efficiency, what we have evaluated was around 65% only. Another thing or the observation from our sides was that all their extractions were in throttle condition. The reason was that because of the heavier deposition in the turbines, the pressure across the turbine was on the higher side and they weren't able to regulate it properly. Because of that, the extraction PRVs were blowing off. The pressure release valves were blowing out. And also, as I have told earlier, the specific steam consumption, the design of which was 4.06, was running high at around 4.9 and 4.48. And if you also see the turbine pressure survey, though it is not the exact indication because all the control valves were in throttle condition, but still you can see some spikes in the turbine pressure survey, which indicates that the overall deposition, the silica deposition in the turbine had happened and the turbine was not working well. So we also, what we did was we analyzed section-wise isentropic efficiency across the turbine. So what we did is we evaluated what was the isentropic efficiency inlet to HP heater first extraction, then first extraction to second extraction, and the second extraction to third extraction, and the third to final extraction. So we divided the turbine into 4 parts, and for each section we kind of evaluated the overall isentropic efficiency, which also indicates that the overall isentropic efficiency across the turbine was actually very low. So to them, we have actually recommended to go for a complete overhaul of both the turbines, check for any depositions, even inspection of turbine internals, control valves and rotor blades, gland ceilings, and if required, do a complete maintenance. What we have heard was that there was some chemistry issues, water chemistry issues, and because of that, silica deposition has happened. I mean, we are not sure about it. That is the feedback what we have received from plant team. So we have recommended to do a complete overhaul of both the turbines because heavy loss is happening in both the turbines. We are estimating around 400 kilocalories of overall heat loss, and we estimate by doing a complete overhaul, at least 15 to 20% of overall turbine performance can be improved. Moving on, I'll talk about another important parameter. For boilers, I said the air preheaters are the heart of boilers. So now I would come to the heart of turbines. I would talk about vacuum. I think if air preheaters are the heart of boiler performance, then the vacuum system or the condenser cooling towers, which overall maintain the vacuum in turbines, are the heart of turbine systems. So in this, I would like to talk about best practices in cooling towers. So what I have done is I have identified few major issues, few problems, and tried to give probable solutions for the same. So in terms of best practices for cooling towers, the first one I would like to tell you is regarding the high cooling tower specific energy. So your cooling tower specific energy is on the higher side, then you can always go for FRP blades. Now, even in FRP blades, there are higher efficiency FRP blades available, which actually improve your specific energy consumption of cooling towers by almost 15 to 20%. I'm talking about FRP to FRP conversion. If I compare it with aluminum or GRP, it would be at least 30 to 40, 50% more. Blade angle optimization is something which can be taken up, especially when you are evaluating performance between different seasons, winter, summers. In winters, your cooling tower requirements are lesser. So in that, you can optimize blade angle. In summers, when you require higher airflow, you can again increase the blade angle and so on. Variable frequency drives, I mean, cement plants need no introduction to this. Most of the plants are actually using it. But again, how you are using it, how you are managing it, what are the control loops you are using is equally important. For cooling tower fans, if you are using a water-cooled condenser, then your condenser outlet temperature could be a feedback. And if you are using a air-cooled condenser, then you can directly give command of vacuum to it. So the VFDs will maintain the vacuum levels in the air-cooled condenser. Next is the fan tip clearances and poor balance. If the fan tip clearances are not good and the balance is not good, then also it will increase the overall specific energy consumption. The next problem regarding the cooling towers is drift carryover of water outside the unit. So in that case, these are the actions you can take. It could be due to uneven operation of spray nozzles, blockage of fill packs, if your drift eliminators are not working well, if your fills are getting choked or damaged. So these are some of the reasons or some of the areas where you can work to improve the drift carryover. And overall lack of cooling and hence increased range is the second or the third problem. So that could be because of recycling of humid discharge or intake of hot air from other sources. It could be again due to blocked spray nozzles, uh, plugging of cooling tower distribution nozzles. If those are not happening on a regular basis, they may get choked. Scaling of the fill pack is another reason for it. You can always go for efficient splash bars, which improves the overall distribution of water in the cooling towers. And you can also check for the desired overflow versus the actual airflow, whether you are meeting those requirements or not. So these are some of the ways you can actually evaluate whether your cooling towers are performing well, and if not, how you can actually improve them. Next, in the same continuation to vacuum systems is the condenser performance. In condenser performance, there are three major issues. One is the high heat load. When I say high heat load, that means there are two reasons for it. One is either there is excess heat getting added to the condenser through your high temperature drain valves, be it steam chest drain, be it HP heater dump or HP steam dump or something like that. So you have to ensure no excess steam or excess heat load is getting added to your condenser. And the other part of it is the overall cooling water flow itself is low. So then you will have to check the flow path of the cooling tower, whether your sufficient number of cooling water pumps are operating, whether your condensers are choked, are not in choked condition, because that will also reduce the overall flow of cooling water into the condenser. Next is the dirty tubes, one of the biggest areas where cement CPPs are facing this issue. Most of the plants where we visit and where we interact, this is a big issue. So in that, you have to go for a regular treatment, a regular cleaning of your condensers. It could be an offline treatment like jet cleaning, bullet cleaning, chemical cleaning, water washing, or things like that. And also regularly check condenser tubes because deposition sometimes erode it. So that also you check regularly. Air ingress, another major issue being faced by cement plants. So for that, you can do condenser fill test, you can do helium leak test. I have also mentioned some of the areas where air ingress is very common, your standpipes, your LP heater drains and vents, welding cracks, condensers below, and so on. Moving to the next part of turbine heat rates is the performance monitoring of HP heater and LP heater. For HP heaters and LP heaters, monitor your temperature terminal difference, and drain cooler approach regularly. Ensure that they are nearer to your design values. If they are not nearer to design values, then in some ways or the other, it is actually impacting your HP heater or LP heater performance. Specifically, LP heaters, you may not notice the difference a lot, but definitely if your HP heaters are not performing well, your TTD levels will definitely change. TTD, as it is called, temperature terminal difference, should be as close to zero, and in some cases even negative is possible. But if it is increasing, let's say to a higher number, 3, 4, or 5, something like that, then definitely the heat transfer has been impacted. So in those areas, check. I mean, you can do during your annual maintenance or something like that. You can check internals of your HP heaters. If the baffle plates are intact, mostly since it is a DM water circuit, so we predict that there will be no deposition as such. But again, checking the internals, how they are placed, and for any sort of depositions will help you improve the HP heater performance. This is again a flow chart which can be followed by plant teams to check the impact of TTD and DCA on their heaters. Whenever I share the presentation, you can go through this and track your performance for HP heaters specifically. Next is auxiliary performance, power consumption. I think cement sector is one of the best sectors when it comes to APC performance. They have a super control on all the major auxiliaries. So I am not spending a lot of time on this. So typical breakup of auxiliary power consumption, a typical breakup of a plant with 8.85% or APC. What are the major equipments? Your BFP, FD fan, ID fan are the major equipments, and the others are also contributing in some manner. So a very brief about the APC, because I feel cement plants are doing significantly well in this area. VFDs is something which cement sector has adopted with, with full conviction. So they support improving the overall APC in a very significant manner. Pumps, fans, compressors, even compressors, you can use VFDs. They have a saving potential of 20 to 30% in improving the APC percentage, especially in today's scenario when there is significant part load operations. They are playing a very big role. Next is utilization of high efficiency equipment. Our chair, Pawan Mathur sir, in his opening address talked about BFP retrofitting. So, I mean, that is something you can definitely move into when you're talking about high efficiency equipments. I mean, usually one big problem what we have observed with BFPs are they are designed at 1.5 times the drum pressure. Because of that, there is a significant mismatch between the actual requirement and the design requirements. So whenever you are considering for a retrofit of your boiler feed pumps, ensure that you design it as close as to your design operations rather than 1.5 times of drum pressure, because that will bring your operating point and your actual operating point and your actual design point closer and will give you higher efficiencies. Another point which is sometimes not that properly implemented in some plants is the control loops. You have installed VFDs, but what is the actual control philosophy behind it? For example, if I talk about drum level control, so what people do is they give a discharge pressure command to the VFD. So the BFP discharge command of, let's say, 125 kgs or 120 kgs will be given to the BFP. But a better idea is that instead of that, you give a DP command. You give a difference between drum pressure and the BFP discharge pressure. You can give it as 8 to 5 kgs. Even I have seen in some plants as low as 5 kgs. So that is a better control of doing things. So what you can do is instead of giving a discharge pressure command, you give a DP command. Same is the case with your condensate extraction pumps. Instead of giving a discharge pressure command to your CP, give a direct dilator level command. Your dilator level is directly maintained by a CP VFD. So that is some things which can be done by plants to improve the overall APC. Then last, we interact and work with a lot of bigger IPPs, and I understand that your operations with cannot be compared to IPPs, but there are always certain things which the CPPs can learn from the bigger IPPs, and I would also say the IPPs can learn from CPPs. For example, the energy management tools. Uh, I mean, it is a very good example of how live tracking of performance can be done. I think many of the cement plants are already doing it. Pawan Mathur sir is sitting here. UTCL is doing it. But the other plants can also slowly and steadily adopt this area where you get live performance of your parameters, live heat rate monitoring, live APH performance, live boiler efficiency calculation. We have to slowly and steadily move into these areas, because I always feel what you can measure, you can control. I mean, it's a cliched saying, but I feel it is really a blessing if you are able to track your performance online. There are several software, several companies available. I have shown you examples of how NTPC has developed an over Pi software. They call it Pi software, which gives them an online measurement of all their major parameters: boiler efficiency, your ID fan power, and specific consumption. I'm talking about ID fan power, draft power consumption, your APC, heat rate, boiler efficiency, and all those things. Another point which I feel CPPs, many of the plants are actually following it, but few CPPs should maybe improve their performance is the DM water consumption. DM water consumption in many plants we have seen has increase to more than 3%. I mean, we are seeing 3.5%, even 4%. DM water has a big impact on heat rate, which is actually missed by many plants. If I talk about some numbers, our estimates tell 1% increase in DM water can increase your heat rate by 15 to 20 kilocalories. So what we recommend is that the plant should target to have a DM water consumption to around 1 to 1.5%. If you can reduce it lower, nothing like that. But 3.5% is too high. You are losing almost 30 to 40 kilocalories when your DM water consumption is around 3% or more. In this case, the IPPs are very strict about it. Most of the plants, their DM water consumption would be in the range of 0.5, 0.6%. They do a complete evaluation of DM water losses. They monitor their drains, drain temperatures, and even a slightest variation in DM water consumption. They are able to gauge whether I mean, this is due to a tube leakage or not. So when you are following a proper monitoring and control of DM water, you will have a lot of advantages, not only in terms of monitoring your DM water loss, but also if there is any any extensivency in the boiler, for example, a tube leakage or not, you will easily or immediately understand my DM water consumption has increased. It must be due to tube leakage. You can prepare a checklist of these sorts where you can have what are the major things which are affecting or impacting your DM water, and then one by one you can go and do a cross check why your DM water consumption is increasing. I mean, before we close, I have a case study on a reduction in coal losses at your yard. Many of the times, the carpet losses, the GCV losses at the yard are high. So this is a case study by JSW Ratnagiri, who have 100% imported coal usage. They import the entire coal which is being used in the plant, and they were experiencing significant coal losses, both in terms of quality as well as quantity. Since they were importing it from port to their plants, there was significant quality loss in terms of loss in GCV, and also your carpet losses and your drift losses and things like that. So they took a complete analysis of it. They tried to reduce the moisture losses and especially the quantity losses during monsoon. They installed coal sheds. Then the loss due to spontaneous combustion was also improved upon by spraying of sodium silicate solution. Then installation of windbreaker to avoid the drift of coal and things like that. So, I mean, you have to understand whether this is a significant problem for you or not. And if it is a problem, then you have to lay down steps, identify areas which are impacting it, and then work on that particular area. Pawan Mathur sir was talking about CFD analysis. The plants can definitely take CFD analysis. I mean, this is a case study I'm taking specifically because we all know about CFD in combustion systems, but CFD can also be worked upon in your in your cooling water pumping systems. Specifically, if you have a bigger CPP and you have a combined cooling water sump system, then if your overall specific energy consumption in cooling water system is really high, then CFD analysis in your complete cooling water pumping system, your forebay, your pipelines which are connecting to condensers, you can do a complete analysis of that and identify areas if that is the case. In this particular case study, the overall head of the pumps were very high. I mean, the pumps were running at very high heads. Because of this, the plant team went ahead and did a complete analysis of CFD in their raw water intake sump. They identified areas of problem wherever there were some turbulence, wherever there were some vortices being formed. So they identified those areas and did a complete rectification, and they were able to significantly reduce their overall problems in the raw water intake sump or the cooling water intake sump. That is also a good area, CFD in boiler combustion, your your cooling water areas. Even if some of the plants are facing problems like boiler tube leakage, it could be one area which could help you evaluate why a particular zone is getting higher tube leakages or not. Lastly, I have listed down few practices in terms of maintenance and reliability, how you can improve that. So preventive maintenance schedule should be followed, regular vibration monitoring, monitoring of MTBF for your equipments, online boiler tube leak detection system, external analysis of all major tube leakages. Whenever there's a significant or a bigger tube leakage happening, send it to an external lab, get it analyzed for the reason of it. Debris analysis of lube oil, ultrasonic leak test in condenser, eddy current checking to check thinning of condenser tubes. These are some of the maintenance and equipment reliability practices, some from CPPs and some for bigger IPPs, which can be adopted if the plant feels the requirement. Then a tripping analysis, YY analysis, why certain trippings happened, and your analysis of your acid tanks, chimneys, whether any steam leakages are there, and some of the other things. I have listed it down. You can always go through it in more details. With this, I would like to end. Thank you, everyone. Thank you for the patience of listening. I hope you have found this session valuable. Sir, over to you.
Yeah, thank you very much. Just for the interest of all, I would like to summarize this. So first, Mehul, you told us about what are the average parameters for 73, taking from 73 TPPs, cement TPPs. So average PLF is around 71%. APC is around 9.25 to 4%. 3273 kilo per unit is heat consumption, and 1.267 kg CO2 per unit is emission level. So my view is that certainly we have certain scope here, and we can definitely reduce this immediately below 3000 for heat rate, APC around 6% in the current context. So we have a lot of scope here. Then you told about boiler efficiency and what are the major losses. Dry flue gas losses 6 to 10%, 0 to 2% in incomplete combustion, and then unburned 1 to 3%. So these are the areas where we can act upon, and these are operational things only. This need not any major capex or anything to do with that. Then you told us about APH performance, importance of leak test, and how APH can be improved. Case study was also shared by you. Then turbine heat rate, major issue means one of the case studies you told, deposition. So deposition is related to water chemistry that you emphasized, and you also told why sometimes it is important to do detailed analysis, isotopic analysis, and to understand at which stage we are having the problem. Then you told us about improving the efficiency in cooling towers. So FRP blades you told us about, and then spray nozzles, whether they are working fine or not. These were some of the areas. Condenser performance, you told why cleaning of condenser tubes is very important. Why it is not good to have the air ingress into that. Then you talked about HP heater and LP heaters. Why it is required to have the consistent performance monitoring of that, and why temperature differences should be minimal. Then you talked about APC and various measures which can be taken for APC reduction. As I told, we have good scope in reducing that at average industry level. 3 to 4% we can reduce taking. My idea is that taking some capex within the ROI of less than 3 years, we can reduce it to up to 6% for CFBC boilers. That is a idea I am having. Then you told us about IPPs, EMS system, then why We should continuously monitor DM water consumption. One major issue you informed that tube leakages. You are absolutely right. We should have very clear alarm configured in the CCR whenever the DM water quantity is going down. Difference of steam and water quantity is going down. So it should immediately speak out a given alarm so that we can save our boiler tube leakage. And then you told us about various maintenance practices in various cement plants. Thank you, Mahel. Thank you very much. Yeah, over to you.
Yeah, thank you, sir. So we have a few questions. I'll just read it out for you. My first question is to the Siemens team. We would like to know the plant team, the few of the conditions I've asked about, what are the minimum specific steam consumptions for a turbine, let's say 20 megawatt to 25 megawatt size, and approximately what could be the heat rate, turbine heat rate?
If I talk about with inlet stream parameter of 64,480, then with water-cooled condenser in regenerative system, generally it has a SSC of around between 3.8 to 3.9. And for ACC, it is below 4 in term of SSC. But heat rate, actually, in the last presentation, I presented with the high inlet stream parameter like 64, 480, 84. I have given the values what Siemens can provide. I will share that values with you.
Yes, sir. It would be helpful if you can give us an Excel sheet.
Sure, sir.
Because many of the turbines are also working at higher levels now. We have even 525 and 85 kg pressure turbines also.
Yeah, it's you presented like it is better to do the isentropic comparison, like chamber wise, stage group wise, and generally we are giving isentropic in between 85 to 88% in this range.
Okay, thank you, sir. Thank you. Our next question is to Atlas Copco team. There are two questions asked to them. One is regarding specific energy consumption for comparison between oil-free and oil-injected compressors.
Mm-hmm.
Mr. Manoj?
Yes. I can hear.
So specific energy consumption comparison between oil-free and oil-injected compressors.
Sir, if you can see if you compare the one-to-one comparison for only compressor, then the specific energy of oil-injected compressor is slightly 8 to 10% better compared to oil-free compressor. It is when you compare only compressor to compressor, but when you compare the complete compressor room layout, then it's a different thing. Like up to 1000 kilowatt, up to 1000 CFM. If you compare, then the ACR of oil-injected compressor will be better. But above that, if you require the oil-injected compressor along with the dryer and filter, and then you compare the compressor layout, then the specific energy of oil-free setup will be much better.
Okay.
So broadly, oil-injected compressor is 8 to 10% better specific power compared to oil-free if we compare only compressor.
Thank you, sir. So there's one more question for you. This is regarding centrifugal compressors. What are the minimum sizes available for centrifugal compressors, and at what specific energy levels? For screw, we know it is around 0.17 kilowatt per CFM. So minimum size of centrifugal compressors and at what specific energy level?
The specific energy is approximately 0.14 kilowatt per CFM for centrifugal compressor, and it start from in terms of kilowatt, it start from 450 kilowatt to 6000 kilowatt, and in terms of flow,
in terms of CFM, they were
in terms of that I'm telling both. In terms of CFM, it is starting from 2500 CFM to 40,000 CFM.
Okay. Okay. Yes, sir. Thank you for your input, sir. Pawan sir, up to you. Thanks.
Pawan sir, if you allow me, I can present just the heat rate values.
Okay, please.
Please allow me to share my screen.
Yeah, just a minute, sir.
Yeah.
Please share.
Yeah, we are just giving you that access. Yes, sir.
Yes. Okay. Are you able to see my screen?
Yes.
Yes, sir.
Basically, it is giving an overview of heat rate values, what we have supplied machine to with these parameters.
Okay.
Like 64,480, it is in the left table, it is given, for example, it is between 15 to 20 megawatt turbine. And it is with the feed water temperature of 200 with 3 bleeds. Heat rate of 2550 bit to 2600 is possible. We have supplied these machines and proved at site. And it keep on reducing if we increase the inlet stream parameters. And this is with the water cooled condenser. And if comes to the air, just a moment. If we come to the ACC, then these values become slightly increased.
Okay.
We can share this slides with you.
Thank you, sir. Thank you.
Yeah, thank you.
Okay. So, Mehul, shall we close the session now?
Yes, sir. We can close with your remarks, sir.
Yeah, thank you. Thank you very much, Mr. Raju from Siemens, Mr. Manoj from Atlas Copco, Mr. Naman from Ecolabarium, and Mr. Mehul for providing good insights on improving the energy efficiency for TPP through various of their concerned contributions. And I thanks all the participants also for listening carefully and raising the questions. Thanks a lot for all to this participation in CIA. Thanks a lot.
Thank you, Pavanji.
Thank you all.
Thank you to all
Thank you.
participants.
Thank you. Yeah.